ME 347, Example 16. Standard atmospheric air is drawn through a frictionless adiabatic converging nozzle into an adiabatic constant area pipe with a length of 2.0 meters, a diameter of 0.10 meters, and with an average friction factor of 0.020. For Part A, sketch the temperature entropy diagram for this flow. For Part B, calculate the maximum mass flow rate through the pipe. For Part C, determine the pressure at the end of the pipe. For this problem, we will assume steady, uniform flow of an ideal gas with constant specific heats. Also, we will assume that the air in the room is at a stagnation temperature of 288 Kelvin and a stagnation pressure of 101 kilopascals. Finally, we will assume isentropic flow in the nozzle with gradual area changes, and then adiabatic flow in the pipe with friction. Note that the flow in the pipe with friction will definitely be non-isentropic. For Part A, sketch the temperature entropy diagram. Before doing so, let's look at a schematic diagram for the flow. Room air at stagnation conditions enters the frictionless converging nozzle on the left and then flows to the right in the x direction through the pipe with constant diameter d and friction factor F from section 1 at x equals 0 to section 2 at x equals L. Thus, for the temperature entropy diagram, the flow begins at the stagnation conditions upstream of the pipe at state 0. The flow then accelerates isentropically along a vertical line until it reaches section 1 at the entrance of the pipe. Since this is only a converging nozzle without a throat, we know that the Mach number has to be less than or equal to 1. Assuming the Mach number is less than 1, the flow then starts to move along the subsonic part of the Fanno line. For Part B, since we are solving for the maximum flow rate, this corresponds to choked flow at section 2, where the Mach number must be 1 and the entropy will be at its maximum. Thus, the specified length, capital L, corresponds to the critical length, L star, where the reference length, just L, is equal to 0. For Part B, we calculate the maximum flow rate corresponding to this choke condition. Before starting the calculations, we note that by conservation of mass for steady flow, we can calculate the mass flow rate at section 1 or section 2, which will be at the critical conditions. For this example, we have chosen to evaluate the properties needed for the mass flow rate calculation at section 1. Then, to begin the calculation, we see from the given information that we can calculate the Fanno flow parameter, F times L divided by D, that accounts for the amount of friction required to get to the choked flow condition. Again, since the flow is choked at section 2 at x equals L, the quantity L star minus L is equal to just the length, L, capital L, for this case. Setting the equation given to this value allows us to solve for the Mach number at section 1. A closed form solution cannot be obtained, so we can either use a figure or an online calculator to get a value. We will use the figure for Fanno flow for an ideal gas with constant specific heat ratio of 1.4 for this example problem. From the legend for the figure, we see that the Fanno flow parameter we just calculated corresponds to the solid black line and the y-axis on the right. For our value of 0.40, we read horizontally over to the solid black line and down to the Mach number of 0.625 for section 1. Again, this can also be obtained using an online calculator for Fanno flow. Once we have the Mach number, we can use it to calculate the actual velocity. To do this, we notice by looking at the temperature entropy diagram that the properties we need to calculate correspond to the isentropic flow through the nozzle. Thus, we can use isentropic stagnation relations for these calculations. First, we calculate the stagnation to static temperature ratio from the Mach number at section 1 to be 1.078. From this ratio and the stagnation temperature, the static temperature is dropped to 267 Kelvin. Then, from the relationship for the speed of sound for an ideal gas and our Mach number, we calculate a velocity of 205 meters per second at section 1. Similarly, we calculate the stagnation to static pressure ratio from the Mach number at section 1 to be 1.301. From this ratio and the stagnation pressure, the static pressure has dropped to 77.6 kilopascals. Finally, using the ideal gas law, we can calculate the density of the air to be 1.018 kilograms per meter cubed. For this calculation, remember to use absolute units for temperature and pressure. Also, use the meter kilogram seconds for your base units to ensure that everything cancels. Using the mass flow rate equation for section 1, given earlier, substituting in the values calculated for the density and the velocity, and using the specified pipe diameter, we get a mass flow rate of 1.63 kilograms per second. This is a huge amount of air. For part C, calculate the pressure at section 2, which for our case corresponds to the pressure for choked flow. Again, looking back at the temperature entropy diagram, we see that we are now performing a calculation that applies to a process along the Fanno line. Thus, we will use the Fanno relations for this calculation. Based on the Mach number at section 1, the static to critical pressure ratio is 1.688. Substituting in the static pressure at section 1, we get the even lower pressure of 46.0 kilopascals at section 2. Before concluding, let's consider how increasing the length of the pipe would change the mass flow rate and pressure at section 2 for constant upstream stagnation conditions and the flow still being choked at the exit. First, we note that the Fanno flow parameter that we calculated earlier would increase. Looking back at the Fanno flow figure, we see that this would lower the Mach number at section 1, moving it closer to the stagnation conditions at section 0. Starting the Fanno line from here, we see that it will now extend out to a higher maximum entropy at a lower pressure at section 2. Finally, if we consider calculating the mass flow rate at section 2, the speed of sound and area are constant, so mass flow rate just scales with density, which decreases with pressure. Thus, the mass flow rate also decreases. To summarize, for the given constrained conditions, adding more pipe or friction increases the pressure drop needed to get choked flow, and the mass flow rate through the pipe also drops, which makes sense for a subsonic problem.